Well, tonight we welcome Dr. Yutaka Hirai, who is a JSPS Research Fellow at the University of Notre Dame. That's a private university. It has a mission to be a powerful force for good in the world, and it's located in Indiana in the USA. Yutaka received his bachelor's in physics from Waseda University in 2013 and his master's and PhD from the University of Tokyo in 2015 and 2018. Yutaka has two astrophysics for Young Astronomers Awards and earned several scholarships. He specializes in the formation and chemical evolution of the Milky Way and dwarf galaxies through high-resolution hydrodynamic simulations. His research has been cited 454 times, with his latest being for his contributions in probing chemical enrichment in extremely metal-poor galaxies and first galaxies. So, let's give Dr. Yutaka Hirai a warm Mexborough and Swinton Astronomical Society welcome.
Thank you very much, Roy. Perfect. Thank you very much. Okay. Okay. Okay, can you see my slide?
We can.
Okay, thank you very much. So I'm going to start the presentation. First of all, thank you very much for your invitations. I'm very honored to be here. So I'm Yutaka Hirai from the University of Notre Dame and Tohoku University. So today I'm going to talk about the formation of the Milky Way and gold-rich stars. So before going to the talk, let me add some my places a little bit. So I'm now at the University of Notre Dame, which is located in South Bend, Indiana, which is near Michigan Lake and Chicago. I also belong to Tohoku University in Japan in Sendai. And actually, my first international travel was to the UK. I actually stayed in the University of Cambridge for a month as a summer student in 2010. That was a very nice experience. So I'm very happy to be here. Although it's online, very happy to talk to you today. So now let's move on to the talk and let me take you to the journey of the Milky Way for the first time. So actually, this is a picture of the Milky Way. I presume most of you have seen, well, maybe all of you have seen the Milky Way. And then, this is actually the picture taken by the Gaia astrometry satellite, which is operated by ESA. As you see, the Milky Way has several structures. That is, at the center, we can see the bulge, which is a spherical component composed of the old stars. And then there is a disk. This is actually the dust rain and some stars are concentrated here. The disk is actually here. And our sun, the sun is also located in the disk. Also, the Milky Way has the diffuse structures around the disk and the bulge, which is called the stellar halo. This is actually very diffuse, but it's very important to study this structure because it is halo composed of the very old stars. So if we can observe the halo stars, we can see the ancient history of the Milky Way. Also, Milky Way has some associated structures and objects like globular clusters and dwarf galaxies, which are also very old stellar populations. This is actually sort of the map of the Milky Way. So let me show the movie of the Milky Way simulation. This is actually one of the highest resolution simulation of the Milky Way and visualized by the specialists. As you see, from the viewpoint of the sun, the Milky Way looks like a disk with a very thin disk, and we can see, the bulge here. A Milky Way actually composed of 100 billion stars, and then with a variety of ages of the stars. And then if we look over the Milky Way by the face on, we can see that the Milky Way is actually the spiral galaxy like this. And the sun is actually surrounded around here. And then you can see some red region, which is called a nebula, that the new stars are actually formed in this galaxy. So first of all, let me talk a little bit about the history of the study of the Milky Way, how we understand the Milky Way, the structure of it. The first person in the history to see the Milky Way by the telescope is the Galileo Galilei. He put his telescope to the Milky Way and found there are a lot of stars, actually. This is actually not a cloud. And Galileo Galilei said that the Milky Way is nothing else but a mass of innumerable stars planted together in clusters. This finding has been greatly improved by the larger telescope, which is actually by William Herschel in 17th century. He observed a lot of stars in the Milky Way and drew a map of the Milky Way. So this is actually the first map of the Milky Way, he thought. And this is actually, at the center, he thought it is sun, and the Milky Way is extended structures beyond the sun. So after the time passed, astronomers began to debate what the Milky Way is. The most important debate was in 1920. It was called Great Debate by the Shapley and Curtis. These two guys discuss the sizes of the Milky Way. So actually, we see some Andromeda galaxy and Magellanic Clouds, and we know that they are actually outside of the Milky Way. But at that time, they don't know whether they are outside object. Shapley show that this Milky Way is actually the entire universe. So the Milky Way is the largest object in the universe, and every nebula and Andromeda also are inside the Milky Way. On the other hand, Curtis argued that the Milky Way is not the one object, but actually it is the part of the universe, but not the entire universe. So he said that the M31 is actually far from the Milky Way. So such debate can be, concluded by the observations of the Edwin Hubble. He actually observed the variable stars in Andromeda galaxies, and then the variable stars has the relation with the brightness and the variability. So we can, by observing the variable stars, which is called Cepheids, we can understand the distance to the Andromeda galaxy. And we found that Andromeda galaxy is actually very far from the Milky Way, and it's actually the outside of the Milky Way. And then he also observed other galaxies, and other galaxies are actually redshifted, which is a sort of the Doppler effect, which is a sort of the consequences of the expansion of the universe. And this is a so-called Hubble's law, which shows that the more distant galaxies are moved faster from us. So his finding eventually confirmed that the Milky Way is just one of the very large number of galaxies. And by large number of observations, Edwin Hubble classified the galaxies in this type, which is called Edwin Hubble's classification scheme, the Hubble's diagram. And for the early type galaxy, he called ellipticals, which is from the number is actually the ellipticity of the galaxies. And the galaxies, those have spirals. He said spiral, and then put the S in front of the galaxy. S, A, B, C is a sort of the structures of how tight the spiral is. And if at the center, some galaxy has a bar-like structure like this. So if the galaxy has a bar, he classified the galaxies as SB or SBA to C. And then we now know that the Milky Way is classified as SBB or SBC galaxy. So this is actually the picture of the Milky Way we acquired during the 20th century. So let me move on to the method how we study the formation of the Milky Way and the formation of the galaxy. So one way to study the formation of galaxy is to observe the large distance. Because the universe is large, if they observe the large distance, the stars from the light from the galaxy means that it's actually from the past. So if we observe the Milky Way-like galaxies to the past, we can know the flow of the evolutionary history of the Milky Way-like galaxies like this. So this is one way to understand the galaxy formation. Alternative way is called galactic archaeology. The galactic archaeology is actually observe the stars, each star in the Milky Way. So this is, the map of the Milky Way I showed. So by using the European astrometry satellite Gaia, we can get the motion of the stars. Also, there are a lot of telescopes in the world, and we can get elemental abundances of each stars that reflects the history of the Milky Way. So by using such an information, we can establish the history of the Milky Way, which is called the galactic archaeology. So these sort of the observations, distant galaxies and the galactic archaeology can be combined by using the supercomputer simulation. Because observations, we can get one snapshot of the one time. So to connect these, we need the simulations. So simulations we can follow from the earliest universe to the present. So by comparing the data of the simulations to the observational data of the Milky Way or Milky Way-like galaxies, we can understand how the Milky Way was formed. So let's move on to the classical scenario of the Milky Way halo formation. As I said, the Milky Way composed of the several structures. Main structures are bulge, disk, and halo. The first object we thought that is the halo structures. And so the scientists actually argued how the halo were formed. The most famous formation scenario is called the ELS model, which was proposed by Egan Leidenbald-Santech in 1962. This is the model that the Milky Way was formed from the gas clouds and the early collapse of the gas clouds. So in this model, there was the proto-galaxy, which is a very massive gas, and then this gas cooled down and formed gradually the stars. And then the gas further contract with the cooling and then formed some sort of the evolving disk or bulge, and this like this. So this is actually from the observations of the eccentricities, which is the orbits of the stars, and the iron abundance of the stars. There was a correlation between these. So it means that the galaxy collapses very short time scale. And they estimated that the formation time scale of the Milky Way was only 100 million years. This is a sort of the most classical model called ELS model. Alternative scenario for the Milky Way formation was called SZ model, which was proposed by Charlet and Jin. They observed the degree of the iron abundance of the globular cluster around the Milky Way. And they found that the iron abundance is constant as a function of the radius from the galaxy. This means that the galaxies are not monotonically evolved, but galaxies are actually formed by the clustering of a similar system. If the galaxies are formed by cluster systems, so the variation of the elemental abundance are not expected to be varied as a function of the radius. So this model, so many protogalactic fragments are there, and these fragments are gathered together and then form the Milky Way-like objects with a time scale of over 1 billion years, which is much longer time scale than the ESL model. So such an argument was concluded by the observations of the Milky Way stars, such as the Sloan Digital Sky Survey, which is a very large survey, which is the telescope in the New Mexico, which observed a lot of stars in the Milky Way and determined the elemental abundances of the stars. Also, as I said, the European telescope Gaia observed the kinematics of the stars, which also preserved the information of the formation scenario of the Milky Way. And they found that the formation of the Milky Way can be attributed to the clustering system, which is similar to the SZ model, but also still AS model arrives because each protogalactic fragment collapses very fast and then forms stars, and then these protogalactic fragments are gathering, then cluster form the Milky Way. So this is a sort of the scenario of the Milky Way formations. The Milky Way was formed by a small system, which is called dwarf galaxy, and then the Milky Way, very large object, has been formed. So let me move on. So we can now simulate the Milky Way's formation. So let me move on to the simulations of the Milky Way's formation. First of all, I'd like to show the picture of the simulations and the observations. I want you to guess which one is the simulations. One is taken by the Hubble telescope. The other alternative one is actually simulated in computers. So I want you to make some, maybe if you can, maybe some actions button in the Zoom. And if you think the left panel is the simulations, please put an action by the Zoom button. Might be, anyway, yes, yes, great, yes. Yeah, okay, great, 2 of them, and maybe there are some in the observatory as well. So if you think the right panel is the simulations, please raise your hand. Okay, great. 1, 2. Well, it's half. Yes, totally half. It's, yeah, it's really nice. So the answer is right one. Right panel is the simulations. So actually we cannot distinguish what the simulations and the observation. Well, maybe the galaxy would be a bit diffuse compared to the observation, but it's actually, we cannot distinguish between the two. So now we have the reality to simulate the galaxy at this level. So by using such simulations, we can understand the galaxy formation. So let me show one of my simulation. So this is the simulation of the Milky Way formation. So this movie is now at the stage of the very early stages of the galaxy. As you see, there are some structures which is actually followed by the dark matter, and then the gas are condensed following the dark matter halo structures. And each gas shows halo, form stars, and then these are gradually gathered together by the gravity. And then we can see a lot of mergers in this simulation. So let's zoom in to one particular forming galaxy in the early stages of the galaxy formation. So as you see, 2 galaxies are now interacting with each other. So these galaxies are forming a lot of stars, and there are a lot of supernova, which is a large explosion event occurs, and then some supernova blow gas away. And then galaxies actually merge and become a big galaxy. At the later stages, so this is actually later stages of the simulation, and the clustering of galaxies has been suppressed, but a lot of gas are accreted to the galaxy to form the disk-like object. And then we can see the Milky Way-like object, which has the disk, bulge, and halos. So this is a sort of the Milky Way simulations. So in the simulations, we compute the gravity of the stars. Just a high school physics. We compute this is for the 2 stars. For the 3 stars, which compute each of the gravity, and galaxy has a billion of stars, and we compute the gravity for the billions of stars. So it takes a lot of, it requires a lot of computational facilities to compute such a large computation of the gravity. Also, in the galaxy simulations, we compute the cycle of materials from the star formation of the gas to the supernova. So in the galaxy, there are cycle materials like this. So there is a star formation from the nebula, and some stars, especially for the massive stars, explode as supernova. And these distribute materials to the interstellar medium of the galaxy, which is like remnants of the stars. And these remnants, again, cool and then form new stars. Such cycle materials actually occurs in the galaxy. And in the simulation, we model such materials, such cycle of materials. In fact, most of the elements in the universe are formed in the stars. So elements are actually distributed by such a cycle of materials. So let me move on to the discussions on the origin of the gold-rich stars. So this is the periodic table of the elements showing the origin of these. Hydrogen and helium, lightest elements, are formed at the first time, the Big Bang of the universe. And then other elements, most of other elements are formed in stars. For example, until the iron, most of the elements are formed by the inside the star or the explosion of the supernovae. But iron is the most stable nuclei, so the heavier elements are more difficult to synthesize. Which requires a lot of neutrons to make the atoms of the heavier nuclei. So that it means that some extreme environment is required. So now we argue that where these elements are coming from, and gold actually are one of the heaviest elements in the universe, and also gold is also very difficult to synthesize. So how we understand the origin of these? So the first step is to observe the elemental abundances. So you might be tested before. If you take the sun spectrum by the prism, and you can see some lines in the rainbow taken from the sun, which is actually the absorption line of the elements exist in the sun. For example, line C is the absorption line of hydrogen, D is sodium, E is iron, and H is calcium. So by using such a line, we can see how much elements are inside in the star. This is an example of the spectrum of the star taken by the telescope. So this is actually sun's spectrum. As you see, there are a lot of the absorption lines by the existence of the elements. And astronomers in 1990s found that some stars are actually have a large amount of gold. Well, gold is actually difficult to observe, so the europium is the similar elements in terms of the nuclear synthesis. And this is the spectrum of the first gold-rich stars the astronomer found called by the Sneeden stars following his name. As you see, the europium, which is similar to gold, is very enhanced in this star. So nowadays, astronomers know that such a gold stars, there are a few percent in the Milky Way. This is the plot of the elemental abundances of the Milky Way stars. So the vertical axis is the heavy element abundance, europium, and the ratio of europium to iron. Europium is a sort of similar element with gold. And then horizontal axis is iron abundance. The iron abundance is a sort of time indicator because the universe was born from the hydrogen and helium. So in the very early stages, the iron abundance is very low. As the time passed, because of the stellar nuclear synthesis, iron abundance will be increased. So the stars plotted left is old stars, and stars plotted in right is the new stars. And as you see from the europium over iron ratio, there are a lot of scatters. And we define that the gold-rich stars from the europium abundance are 5 times larger than the sun, which is plotted with a red. So we might, by carefully analyzing these stars, we can understand the origin of these stars and might have, because these are iron abundance is very low, which is very old stars. So by using these stars, we might have understand the Milky Way's formation in the early phases. So the nucleosynthetic study has shown that the origin of the gold would be the neutron star mergers. Neutron star merger is a sort of the merging of this very compact object called neutron stars. Neutron stars is a remnant of the massive stars explosion, which consists very dense, which only have the neutrons inside, and which means that the environment of the neutron star merger is a very, very neutron rich. And this is actually sort of the most extreme environment of the nucleosynthesis. In such a neutron star mergers, there are a lot of gold produced. So by assuming this object as a source of the gold and the europium, we can compute the galaxy formations. So we have computed the Milky Way's formation by assuming the neutron star mergers as a site of the heaviest element. So this is the figure, the similar figure I showed before, and the color from purple to yellow is a simulated stars, and the orange is the observed stars. And gold-rich stars are within the red, above the red line. And simulations by assuming the neutron star mergers as a site of the heavy elements also shows a few percent of stars in the Milky Way are gold-rich. So from these simulations, we can know when the stars are formed. From observation, it is just a snapshot. We cannot get when the stars are formed. But we can analyze from the simulations the time of the stars, each star formed. So this plot shows when the stars are formed inside the simulations. And color coding is all stars in the simulations, and red plot are the gold-rich stars. And this is the horizontal axis is the formation times of the stars from the beginning of the universe to the present. And the vertical axis is the iron abundance. And as you see, the iron abundance increases as a function of time. And notably, the gold-rich stars are concentrated in the very early stages of the galaxy formation. Which means that if we see the gold-rich stars, these actually are formed in the very early stages of the galaxy formation. And as I showed before in the simulations, in this stage, these galaxies are formed in the dwarf galaxies accreted to the Milky Way, like this. So this is the most famous merging event to the Milky Way. There was 10 billion years ago, there was a merger of two galaxies. So gold-rich stars would be formed in such a small system and then merged to the Milky Way. And now it is mixed. So we cannot distinguish, but we can distinguish from the stellar abundances. So the merging history of the Milky Way, by using the chemical abundances, the elemental abundances, and the kinematics, we know some merging events like this, some names from Gaia, Enceladus, or something like Kraken, or something like this. So these merging events has been identified over about 10 billion years ago. So actually the Milky Way are formed with a lot of merging event, and we found that most of the gold-rich stars are coming from some of these merging events of the Milky Way in the past. So after experienced the merging events of the Milky Way, so they start to form the disk, including the sun. Let me show. Okay, so the early formation is actually the merging events. So this is the place where most of the gold-rich stars are formed. And later on, there are the starburst phase of the galaxy. So which is because of a lot of mergers and the gas compression, the stars are very actively formed inside the Milky Way. And then they have the merging event has been suppressed because the galaxies are developed and the universe are expanding. So the galaxies are a little bit isolated, and then gas are created to the galaxy to form stars, and then begin to form the disk-like objects. And the latest stages, which is very secular evolution, like the disks are developed by the plane, by formation of the stars by the disk itself. This is a sort of the scenario of the formation of the Milky Way. At very early stages, the Milky Way was formed from the old star with a dwarf galaxy, which has a lot of the gold-rich stars, and then the dwarf galaxy merger suppressed on the later phases and to form a disk-like object like this. So by looking at the elemental abundances like gold-rich stars and then kinematics, and the simulations, we now know that the Milky Way are formed from like these. So now we got such structures of the Milky Way with a bulge disk. Bulge is similar to the halo and halo with a lot of the gold-rich stars. Okay, so this is a sort of the scenario of the Milky Way formation and the gold-rich stars. So now let's move on to the future of the Milky Way. What the future of the Milky Way is. Now, from the simulations, we can predict the future of the Milky Way as well. As you know, our neighbor is Andromeda Galaxy. This galaxy is the largest galaxy in the nearby universe. And we know that the Milky Way and Andromeda galaxies are gravitationally interacted with each other, and they are getting closer and closer every year. So later times, after more than 5 billion years later, we think that the Milky Way and Andromeda galaxy will be merged. Let me show the movie of the simulations of the galaxy mergers. So this is a model of the two spiral galaxy like the Milky Way and Andromeda galaxy. So this is actually after 5 billion years later, the Milky Way and Andromeda galaxy are getting closer and closer and then get merged. But the galaxy is very diffuse, so even if the galaxies are merged, each stars do not merge. So once they cross by, and then firstly they pass by because they have the inertia. So, and then another gravitational interactions has been getting closer of the two galaxies, and then the galaxy will be merged. So at the time of the mergers, gas clouds are condensed. And so there are a lot of star clusters are formed like this. So we can see a lot of star clusters here, here, and here. So this is a very dramatic event. So the two galaxies merge, like the Milky Way and Andromeda. There are another starburst in the future. And so there are a lot of stars are formed, and there are a lot of supernova occurs at the time of the mergers. And as you see, the spiral structures, beautiful spiral structures in the Milky Way and the Andromeda galaxy are totally destroyed by the merging of the two galaxies because this merging is too violent. And some stream-like structures like this from the galaxy remnants here and here. And eventually, the galaxy becomes the elliptical galaxy like this, which is The astronomers once thought that it was early type galaxy, which we still called it as early type galaxy, but actually this is formed later. The elliptical galaxy, very big elliptical galaxy can be seen. So at this stage, if we live in this galaxy, we cannot see the beautiful Milky Way, but we just see a lot of stars throughout the sky. Maybe we are lucky, we can see a beautiful Milky Way now. So this is a sort of the entire scenario from the early universe to the Milky Way, to the future. The Milky Way was formed from the clustering of the smaller system, and then later, the gas accretion creates the beautiful spiral disk. And then the Milky Way and the Andromeda galaxy will merge and get the large elliptical galaxies. This scenario can be seen by the chemical elemental abundances like the gold-rich stars and computer simulations. So at the last of the talk, let me show some future plans of the telescopes and simulations. So this image is our, extremely large telescopes planned in Europe, including the UK, which has 40-meter diameters. Well, as you know, the first telescope by the Galileo Galilei was only 4 centimeters. So now we are planning the 40-meter diameter telescope. There are 3 planned extremely large telescopes like this. This is the one in Europe, which is building in Chile. And there are 2 in the US and the international collaboration, including Japan, one is 30-meter telescope, the other one, the Giant Magellan telescope. Both has a diameter of 30 meters. So these telescopes will be operated in 2030s. So maybe about 10 years later, we can see, very deep into the universe. Or maybe we can see the very detailed elemental abundances of each stars of the Milky Way by using such extremely large telescopes planned in the world. Well, the Europe is building now works very nice. So it starts the building. So their plan is ahead to the US. US now still planning 2 of the telescopes. Also, the advancements of the computers are also significant. These are pictures of the world's fastest supercomputer, Frontier in the US and the Fugaku in Japan. So by using such as supercomputers, we can compute the entire history of the galaxies. So as I showed in the galaxy simulations, each stars cannot be resolved. The stars in nowadays simulations are sort of the large mass with 1,000 times than the sun. So each star in the model of the simulation is very large now. So we cannot model each star. But by using such a supercomputer, we expect to resolve individual stars in the Milky Way. So we actually get realistic, formation history and then of the Milky Way by using such a simulations. So we are planning such a simulations. This is one of our simulation of the star cluster formation with the size of stars. So this is simulations start from the nebula of inside the galaxy. And at the time of the gas are condensed, each stars are formed. So these nebula have the element including gold. So each stars are formed with such a gas. So the elemental abundances seen in each star reflect the elemental abundances of previous nucleosynthetic events of the galaxy. So by using such extremely high resolution simulations, we can resolve individual stars and then understand how each star of the Milky Way were formed. So this is a bit earlier, but let me conclude my talk. This is simulations and observations actually enable us to extract the fossil records imprinted in stars. And the formation of the Milky Way can be attributed to the merger of the numerous small galaxies. And most gold-rich stars are formed in the very early universe in such a small fragment of the galaxies. Okay, so thank you very much for your listening. So if you have further questions, please let me know by the email, and also welcome the questions now. Thank you very much.
Thank you very much, Yutaka. If you'd like to just drop your screen, and we'll start to see if you can see everybody else. If anybody online has got a question, would you like to do raise an electronic hand, so I can actually see you? Right, gallery, yeah. Okay, so I've got a question straight away from Mick Nichols. Mick?
Thanks for that. The large and small Magellanic Clouds, are they galaxies in their own right, or are they formed from past galaxy impacts with the Milky Way?
Yeah, actually, the Large Magellanic Cloud is a different galaxy from the Milky Way. So nowadays, we are still arguing that, but the Large Magellanic Cloud is the first falling stage. So if it is correct, the Large Magellanic Cloud was formed in the distant places of the Milky Way. Now it's accreted to the Milky Way nearby. So that we see. So that Large Magellanic Cloud is a sort of very different galaxy from the Milky Way.
Thank you.
Thank you.
Thank you. I've got a question while I'm here. What role does globular clusters have in galaxy formation?
Yeah, that's a very important question and also we don't have an answer. So it's actually the most hot topic that we want to answer. Actually, as you say, that globular clusters composed of the old stars, which means that it was formed in the very early stages of the galaxy formation. But the origin of globular cluster is not well understood because the galaxy has a dark matter, which is called halo. Actually, these are formed, simulation can reproduce the formation of a galaxy. But the globular cluster do not have a dark matter. It composed only by the stars. So we don't know how the globular clusters are formed. Well, one possible scenario is that the globular clusters are formed at the time of the merging of the galaxy. As I showed the simulation of the galaxy merging, there are a lot of star clusters are formed. So this is actually at the time of the mergers, a lot of gas are compressed, and then a large bunch of stars are formed. So at the time, in the old universe, there are a lot of galaxy mergers, so a lot of gas clouds are compressed and then form the globular clusters. So that was one of the possible scenario of the globular clusters. But to be honest, we don't know how they were formed. So it's actually the hot topic in the astronomy now.
Thank you very much. We have a question from the observatory. We have a hand raised there.
Hi, can you hear me?
Yes.
Yeah.
Yeah, fascinating talk. Thank you.
Thank you.
Do we know if any of these gold-rich stars have exoplanets around them? And if they do, does the gold-rich star affect the type of exoplanets that are formed?
Yeah, actually, well, that's also an important question. We haven't discovered the gold-rich stars with exoplanets because exoplanets are usually found in very nearby to the sun. And at the nearby universe, the stars formed in the disk, which is gold-rich stars are rarely formed. But the gold-rich stars are formed a bit distant from the sun, which is very old. So, the observational technology cannot achieve the detection of the exoplanets of the gold-rich stars. But it's really interesting to find the exoplanets in the gold-rich stars. Yeah, maybe I hope that future such a star, the exoplanets will be detected in such a gold-rich stars.
Thank you. Anthony Hood, do you have a question?
Hello, yes, thank you. Regarding the simulations, I assume there are other teams doing these simulations, and I'm wondering how much they all agree with each other.
Yes, so yeah, in terms of the simulations, we need to agree with how much stars are formed in the each halo of the simulated galaxy. So the agreement is that the number or mass of the stars are formed in the simulation would be similar among the different groups. But yeah, such a global properties have an agreement with how much stars are formed. But yeah, for example, the detailed evolutions, for example, when the disk are formed or when each galaxy are assembled, which is actually the different each of the simulation. So we don't know such agreement. So that should be compared with observations and then to understand which one would be better.
Thank you. What about AI coming into this?
Oh, yes. AI is actually, we are working on AI, how to incorporate into the simulation. So as I said, the simulation need a lot of computational power, but AI, we expect the AI will reduce the computational necessity. For example, a galaxy formation simulation need to resolve very small scale with the formation of stars, but also we need to compute the very large scale of the cosmology with a billion of light years. But AI, so the most computational expensive thing is that the place where the most dense region, like the star formation region. And now we are expecting the AI can replace the computation of the star formation and then put into the simulations. So in the simulations, so AI simulates these small regions so that we do not need to simulate such a small region anymore, so that we expect that computational efficiency will be better, and then become more computationally efficient and more higher resolution simulation would be possible by incorporating the AI.
Right, well, thank you.
Observatory, we have a question from you. You were next in line.
Tony Morris, I think, had his hand up.
Trevor.
Yeah, I'm fascinated about the simulations, and I just wondered if black holes were factored into the simulations. I presume Andromeda must have a massive black hole at the center. And I just wondered whether you did simulations with and without, different sizes of black holes, or etc.
Yeah, it actually depends on the simulation groups. So yeah, and each of the simulation, well, galaxy formation simulation is a sort of the entire universe simulation. So we need to make a model of each of the black hole and Andromeda galaxies and so on. So this depends on the simulation project. So for example, one project put the black hole at the center of the galaxy if the mass accretion exceeds some critical mass, and then assume some black hole formation and feedback. And some projects do not assume such accretion, but instead some merger of stars, like our project actually assumed the higher resolution one, not the galaxy formation, but assume the merger of the stars and to form the black hole. So yeah, actually in each simulation has a model of each phenomena of the galaxy. So like that. So yeah, as I said, that the properties of galaxy are in general agreement, but such a sort of the black hole star formation and the supernova modeling are different among each of the galaxy groups. That is a sort of still we are comparing what is a better modeling and so on.
Thank you.
Peter Lloyd.
Yes, hello, Yutaka. Thank you very much for your talk. I'm puzzled as to why most of the gold-rich stars were formed very early in the history of the universe. One would have thought it would take a long time for the gold to build up, since it's been synthesized in only the most massive stars. Is it that the early stars were much more massive than on average, they are now, and they therefore evolved much more quickly? I would imagine they're all second, third, fourth generation stars, are they, the gold-rich ones?
Yeah, that's the key point of our paper. Why the gold-rich stars are formed in the early universe is because of the gas mass of the galaxy. So, assuming that one event of the gold production, which is the neutron star merger or some events, produce a large amount of gold. So, if the gas mass is very small, the entire galaxy has been enriched by one event. So in such an environment, a lot of gold-rich stars can be formed. But if the gas mass is too large, which is a later stage, if one gold-rich gold production event occurs, but the abundance can be diffused to the other interstellar medium, so that gold-rich stars are more difficult to form. So that's why at the early stages, the galaxy is very small, and then gold-rich stars are, easy to form in the early stages. That's why,
I think I see this, that the early galaxies were much smaller, and therefore the density of stars within those galaxies was higher, was it?
Depends on there, yes, but some of the
necessarily,
galaxies,
no.
have the, yeah.
Yeah, I see. Okay, I think I've got it. Thank you.
Right. We'll take three more questions. So, Ian Hargreaves.
Yes, hi. Thank you for the talk, Yutaka. Can you tell me how close are the nearest gold-rich stars to our sun?
Oh, that's a good question. Yeah, the closest one is, I don't know the closest one, but gold-rich stars we can observe within the 5 kilopascal, which means that a few thousand light years. Within like few thousand light years, we see in the gold-rich stars. So yeah, in general, which is near. So yeah, I don't know the nearest one, but most of the gold stars we can observe is within the few thousand light years.
Right. Okay. Thank you.
Thank you. Gregory McNiff, please.
Thank you very much. I just wanted to ask, did the James Webb Telescope independently verify the thesis on the gold-rich stars? And then you touched on this slightly related topic. Because the Milky Way, I guess, is a disk galaxy, for those type of galaxies, does the merging happen before the disk is formed or after? I'm just trying to understand that sort of life cycle of a galaxy with a disk relative to how it merges with other galaxies.
Yeah, that's really what I wanted to do, but unfortunately, JWST do not have instruments to observe the gold-rich stars. Instead, Hubble telescope can confirm the existence or more detailed chemical abundance of the gold-rich stars. And recently, US group has found the very detailed abundance of each element of the gold-rich stars by the Hubble telescope. So by using Hubble's telescope, we can confirm the existence of gold-rich stars. Instead, JWST can as you said, directly observe the distant universe. And instead of the gold, they can observe the lighter elements such as nitrogen and carbon. And then astronomers found that some galaxies are very enhanced in nitrogen, which will be related to the explosion event inside the galaxy. And then we are now arguing the connection between the formation of the early stages of Milky Way and the observed distant galaxies by the JWST. I hope JWST would have some instruments to confirm the gold-rich stars.
No, that's great. And just my follow-up, in terms of the disk galaxies, does the merging with other galaxies happen before the disk or the the ring is formed, or how does that work? Like, how does it in that disk while still merging?
Yeah, if the disk, the merging is too violent, disk will be destroyed, as I showed in the simulation. So disk galaxy is a sort of the more isolated compared to the elliptical galaxies. And when it is formed, we are arguing, JWST actually found the disk galaxy in a very distant universe, which is very past. So some galaxy would have a disk in the very early universe. So yes, but the Milky Way would be later stages.
Great, thank you.
Thank you.
Okay, and final question from Lawrence, from Loz.
Hi, it's not a question, it's just I was a little bit late and I just wanted to thank Dr. Hirai for his talk this evening.
Thank you.
And apologies that I was unfortunately travelling, so I came in a little bit late, but I did catch only about 5 minutes late. And thank you very much. I really, really did enjoy it. So thank you very much for presenting to us.
Thank you very much.
Well, ladies and gentlemen, we've worked Yutaka very, very hard. If those online would like to unmute themselves, those in the observatory as well, let's raise a big hand of thanks to Yutaka for tonight's talk. Thank you very much.
Thank you.
Thank you very much. I appreciate it.
Thank you.